Hello, this is Vodcast number 6. We're continuing with chapter 2 of fluids. We're talking about fluid statics today. And today specifically we're going to talk about the measurement of pressure. For those of you that have taken thermodynamics, this will seem quite familiar. It's manometry, which we covered in section, I think it was in chapter 2 of our thermo book. But we're going to go through it again. Section 2.4 is about something called the standard atmosphere, which we'll discuss a little bit. And then you'll notice there's a little bit of change from what I said on the last vodcast. I said we'd go from sections 2.4 to 2.6. But when I looked in your textbook, I realized that 2.7 really doesn't have any executable content for the student. It just talks about the mechanical methods of manometry. So it's more fitting to put it with this section. So this vodcast actually covers 2.4 through 2.7, and the next will be 2.8 through 2.10. So and then the last one will be 2.11 and 2.12. So the only change is the interface between vodcast number 6 and vodcast number 7. All right, so the first thing that we talk about in section 2.4 is the standard atmosphere. And basically, the standard atmosphere is just a name for a set of conditions that we consider an idealized set of conditions or a default set of conditions for executing problems. And basically, when we talk about conditions, we talk about temperature, pressure, density, specific weight, and viscosity. That would be the dynamic viscosity of air. And we use them at sea level, and then as we go up in altitude to different heights, we use this as a default. Sort of like we say room temperature is 23 degrees centigrade unless we have better conditions, or barometric pressure is 101 kPa. So in the standard atmosphere, we begin the textbook on page 50. And I'll just telescope into this, and you should be able to see this in your own textbook. But you'll notice that these are the conditions in both the SI system and the British gravitational system for the properties at sea level. So we have temperature, 15 degrees centigrade, 288 degrees Kelvin, and the equivalents in Fahrenheit and Rankine. We have a pressure in kPa and also in pounds per cubic foot, or excuse me, pounds per square foot, pounds per square inch. Density, acceleration, excuse me, specific weight, and viscosity. Okay, and basically it also assumes that the acceleration of gravity at sea level is 9.087, which we usually round that to 9.81 meters per second squared, or 32.174, which we usually round to 32.2 feet per second squared. Now, the important part about the standard atmosphere is you'll notice that we have a change in temperature basically based on altitude. So when we're here at, you notice this is an altitude of 0 kilometers above sea level. So here is our temperature of 15 degrees and 101 kPa. This just graphs temperature, but just basically explaining the nature of the chart. Then we go through the troposphere, which is up to about 10 kilometers. And you'll see that we have a linear relationship where temperature decreases to a value of minus 55.5 degrees centigrade. In the stratosphere, that temperature remains constant. And then when we leave the stratosphere, you'll see that we have a gradual increase up to an altitude of about 32.2 kilometers. And then we have a more rapid increase up to an altitude of 47.3 kilometers, at which time it becomes constant at negative 2.5 degrees centigrade. All right, so we also have some values for pressure at each of these points, and it makes sense that the pressure would be a maximum here and would decrease as we go up in altitude. There's less of a column of air pushing down on us at higher altitudes as we go through the troposphere, the stratosphere, and up into the upper atmosphere. And so it makes sense that the pressure would decrease. Now, each of these you can tell is a linear function. So in your textbook, you can see that we have an equation which is basically a linear equation, T equals TA plus beta Z, where that's referred to as the lapse rate. Beta is referred to as lapse rate, but basically this follows the equation y is equal to, this would be b, I guess, as in the y-intercept plus mx, right? So what I'm saying is this is the equation, this is a linear equation, the formula for a linear equation. So the slope of the line is minus lapse rate. The variable term that we're functional on is z, or elevation, and TA is the temperature at sea level, where z is equal to 0. All right. Now, if you continue and you look at pressure, it's not necessarily a linear relationship. It's not shown on the graph above, but this is the equation that will give you pressure at altitude based on absolute pressure at sea level, or at z is equal to 0. Right? So these values, some of the values are also defined in your textbook in tables C1 and C2 in Appendix C. So these are the values that you will use in the absence of being given other values. So these are your defaults. All right. So if you're given better data, you will use better data, but if you're not, these are the values you will default to. All right, continuing on with section 2.5 and 2.6, we talk about the measurement of pressure, and also 2.7, sorry, pressure, and the measurement of pressure is referred to as manometry. Okay, so once again, for those of you who have had thermodynamics, this will be familiar. For those of you who have not had thermodynamics, this will not be familiar. One important thing to notice is we typically measure pressure in different types of units. We know that the dimensions of pressure are force per area. So we know that we can measure it in pounds of force per inch squared, which is a PSI. Can measure it in a Pascal, which is a Newton per meter squared. Or we can measure it in some sort of a laboratory unit, such as atmospheres. And sometimes you will see pressure measured in units of height of a fluid column. And this is a real empirical type of a unit. So in other words, what this means is, if you have a particular fluid, pressure on that fluid will cause it to rise to a certain level. That's based on the pressure behind it, and also based on the weight of the fluid column. This is why, one of the reasons why mercury is a good gauge fluid, because it's quite dense. It is 13.6 times as heavy as water. So that means that it takes a column of water 13.6 times as high as a column of mercury. Another reason that mercury is a good fluid is that wettability property that we talked about. That mercury is a non-wetting fluid, so it doesn't tend to leave a film on the inside of a measuring tube, a capillary tube, and also its vapor pressure keeps it in the liquid phase. It doesn't vaporize or boil, basically, in standard types of operating conditions. So it tends to stay, the integrity of mercury stays together, and you need a shorter column than you would for water. So basically, when we talk about pressure, we are concerned with basically three different kinds of pressure. We talk about atmospheric pressure, gauge pressure, and absolute pressure. Okay. And atmospheric pressure is the weight of the column of air. That's when we say atmospheric pressure or barometric pressure at sea level is 101 kPa. Well, it may or may not be. Pressure goes down if there's a storm. It goes down, of course, if we're not at sea level, and so forth. Gauge pressure is the pressure, literally, that a gauge will measure. So, in other words, if you have a tire pressure gauge and you just hold it in your hand, it will register 0. So it does not include atmospheric pressure. And absolute pressure is just barometric pressure or atmospheric pressure plus gauge pressure. So if you have a vacuum, absolute pressure will actually be lower than gauge pressure. If you have a, well, that's not really accurately stated. If you have an atmospheric pressure, a vacuum pulls against that. So the absolute value is going to be still greater than 0, 0 or greater. The gauge pressure for a vacuum can be a negative number, but it's never going to be of a higher absolute value than atmospheric pressure. But, so in other words, I should say pressure atmosphere plus or minus P gauge. All right, so now when we talk about measuring pressure in inches or in a height of a fluid column, pressure can be measured as a height of a fluid column. And this relates to the idea that we covered last time, which was that we have a hydrostatic gradient. dP dz, sorry, I should put z, is equal to minus gamma. All right? So what we basically can say is that if we have P2 minus P1, that's going to equal gamma times Z1 minus Z2. That would be, or I guess what I wrote up before was P1, P2, Z2, Z1, like that, for an incompressible fluid. So you can see that just logistically, a compressible fluid would be a difficult thing to use as a gauging fluid. But what this means is, quite literally, is that you can, if you know the weight of a fluid and you know something about the height of the fluid column, you can pretty much directly, it pretty much directly results as a pressure change. So pressure can be measured in, for example, millimeters of mercury, feet of air, inches of water, etc. Okay, so those are literally measurements of pressure based on the height of a fluid column. Now, when we measure the atmospheric pressure, we use a device called a barometer. And historically, a barometer consisted of a mercury bath, which we now know is not a real healthy thing to have sitting around on your table. But you would take a mercury bath and you would invert a capillary tube that was closed to the atmosphere above it. Well, what happens then is that the pressure of the atmosphere pushes down on the mercury bath and causes the mercury to rise based on that capillary surface tension effect to some level H above the surface of the bath, and that height of mercury is actually the atmospheric pressure. So if you were to use water, if atmospheric pressure, a standard atmospheric pressure might be, well, let's not say standard atmospheric pressure, but if you have something that would be, let's say, 10 inches of mercury, because mercury is 13.6 times as heavy as water, it would take 10 times 13.6, or 136 inches of water to register the same pressure. So this is one reason why mercury is a very good gauging fluid. The toxicity effect of mercury notwithstanding, there's a lot of reasons why it's used in gauges and why it's a very good gauge. Now, when we talk about manometry, barometry, or using a barometer, measures atmospheric pressure. Manometry is the process of measuring a fluid's pressure using other fluids. Measuring pressure using fluids. All right. And there are two concepts that are very important. Basically, a manometer, if you're measuring the pressure of a gas, say here at point A, this type of a manometer is called a U-tube manometer for obvious reasons. And basically the gas, however hard it presses, will press against whatever this fluid is and bring it to some differential level. So in other words, if you have some height of fluid here, we could call that H1, and then we have this fluid which operates continuously to some other point. We could call the difference between those two H2, and then we're open to the atmosphere. All right? There are two basic principles that govern manometry. One is that the pressure at this interface from the gas and on the fluid are going to be identical to each other, as is here. If this is open to the atmosphere, that means that the pressure right here must be equal to the pressure of the atmosphere. It has to be, otherwise it would rise or fall. Because pressure in equilibrium, the size of the tube is the same, so the pressure acting down has to equal the pressure acting up. Now, we also know from the last problem with the hydraulic lift that the pressure, even if the sizes of the tube were not the same, the pressure is going to be the same. But it stands to reason, if you think through this in your mind, if it wasn't equal, it would move based on what it took to put it into equilibrium. So the fact that we've drawn it this way indicates that the pressure at this interface has to be equalized. Pressure here and here have to be the same. And the pressure here from the gas onto the fluid also have to be the same. Not the same as this, but the same as each other. All right. The other principle is that the pressure increases with depth. And that is called, as we said last time, the hydrostatic pressure. Hydrostatic pressure increases with depth. That means that the pressure here plus some gamma times z is going to be the pressure here. And that just goes along with the whole idea of what hydrostatic pressure means. So let's take a water bath, like just a lake or a cup of water or whatever. This symbol is used to express that we are open to the atmosphere. That means that on this lake or river or cup of water, that the pressure at the interface between the water and the atmosphere has to be the same, so that the pressure here is equal to atmospheric pressure. Now, if we use water, as we go down in depth, the pressure here is going to be the pressure at the surface, say equals P atmosphere. So the pressure of the atmosphere plus gamma times z. The specific weight of water times the depth. All right, so it turns out this is called gamma z. Gamma, is called negative gamma, if you want to be exact, is called the hydrostatic gradient. So if you have an incompressible fluid, you can say, for example, water, pressure in water increases with depth. And in British gravitational units, it turns out that pure water, 0.433 psi per foot is the hydrostatic gradient, meaning that the pressure of an object submerged under a column of water will increase by an amount of 0.433 psi per foot. Now, if you register that 14.7 is atmospheric pressure, roughly, and you take this number and divide it by this, you will see that at about 30 feet of depth, you'll be experiencing 2 atmospheres of pressure. So for every 30 feet, you increase the pressure on an object by about another atmosphere. Okay. All right. So if we take this idea in a manometer and we wish to measure pressure, we can start with an interface here. And we can say the pressure here is equal to atmospheric pressure. So that means if this fluid is continuous, if there's a height differential from here to here, the pressure here must be the same as the pressure here or a little bit higher. So whatever this H2 is, gamma H2 is the increase in pressure. So the pressure at this interface is, let's call that pressure at 1, is equal to gamma times H2 plus pressure of the atmosphere. And since this and this are at the same level, the pressure here is also equal to pressure 2. And what is that equal to? Well, if there's a height 1 here, we could say that we need to subtract out because this pressure is actually higher than this pressure. So to get to the pressure in the gas, we need to subtract out the gamma of the gas times this H, which is H1. All right, so the principle then is interfaces have the same pressure, and as you go down, pressure increases, where gamma Z is positive, and as you go up, gamma Z is negative. The other principle that I hope is obvious, is we're talking about Z direction. So what that means is depth only matters. Do you remember in the first section, we talked about the fact that there's really no pressure gradient in the horizontal directions, either from back to front or side to side. So what that means is that if you have an inclined manometer, which sometimes you will just because it's easier to get a different height of a column at a lower height this way, or sometimes you need to fit a gauge into a particular arrangement. But if you have a level of fluid here, you're really only talking about Z, the Z measurement, which, if this angle is theta, is the length of the tube, which the length of the tube turns out to be the hypotenuse, doesn't it, times the sine of theta, length times the sine of theta. Okay, so you're only talking about the vertical direction when you discuss pressure measurement. All right, I'm going to work a problem for you with an inclined tube manometer in just a moment, but I just want to really briefly talk about section 2.7. And 2.7 just talks about mechanical and electronic pressure measuring devices. Okay. Now, the deal is when we talk about there we go. When we talk about, there are other types of pressure measuring devices. For example, we have tire gauges. Also, you can have a board-on-tube gauge, which is just the kind of gauge that you might have in a car. If you have an add-on set of gauges, a round set with pressure numbers on them, they'll always measure gauge pressure. So if you're looking for an absolute pressure, then you have to add in the atmospheric pressure. Now, the other thing about gauges is they're always indirect measurements. A manometer is a direct measure of pressure in that you're getting a column of fluid. With different types, with mechanical or electrical gauges, you're always talking about some sort of an indirect measure of pressure, although sometimes they can be as good or better than a manometer. But manometers, as you can see, because you need glass tubes and columns of measuring fluid like mercury and so forth, they're not overly practical. So in many, many applications, a different type of mechanical or electronic gauge is preferable to an actual manometer. All right, so having said that, I'm going to work a problem for you so that you can take a look at how this works. All right, so getting back to our table, let's take a look at problem 232 in your textbook. All right, in problem 232, we have an inclined tube manometer. And basically what we have is we have a bubble that contains water. We'll call that A. And the interface of the water and the measuring fluid is 3 inches above the center of the bubble. We then have this measuring fluid, which goes up an inclined tube, and the length of the inclined tube is 8 inches to the interface, which of course is going to be horizontal. All right, and we're told that the specific gravity of our measuring fluid is 2.6, meaning that it's 2.6 times as heavy as water, and that the angle that the inclined portion of the tube makes with the horizontal is 30 degrees. All right, now at the end of this measuring fluid, we have another bubble of water, which we call B. And we're told that the height difference from the center of the water bubble to the top of the measuring fluid column is also 3 inches. So the problem reads, for an inclined tube manometer, the pressure in pipe A is 0.6 psi. Okay. The fluid in both pipes A and B are water. Did I make a note of that? Yep. Okay. And the gauge pressure in the manometer has the gauge fluid, pardon me, has a specific gravity of 2.6. What is the pressure in pipe B corresponding to the differential reading shown? All right. Well, as you can see, the water in pipe B is higher than the pressure in pipe A. So what that means to us is we would expect that the pressure in pipe B will be lower. Remember, because as you go down in depth, you increase pressure. All right, so we don't know how much lower, but if this is 0.6 psi, we expect this number to be different than that. So let's work out this problem. Let's put in our variables based on this idea of manometry. All right, so we start with the pressure at A. And to go down to the water, we're going to add the specific weight of water times this height differential of 3 inches. Okay. Then what we're doing is we're going up with the measuring fluid. So we need the specific gravity of the gauge fluid, or the measuring fluid, multiplied by this height, which is unknown. But we know that it's 8 inches times the sine of 30 degrees, don't we? So we're here, we start here, we come down to here, so this plus this is the pressure here. Then we go up to here, so this plus this minus this is the pressure here. And then all we have left is to get up to the pressure at B. So I have minus gamma, this fluid is water, times this distance, which is 3 inches, and that will be equal to the pressure in pipe B. All right, so we have a good equation. We went positive goes down, negative goes up, and we took into account the inclined portion of this tube. Now, at this point, we need to talk about what our units are going to look like. And if we want everything to look like, we're told that this is 0.6 psi. PSI is a pound of force per inch squared. So if we put this in pounds of force per inch squared, we need to think about how we're going to put our specific weight of water and the gauge fluid in. So if you look in your textbook for the specific weight of water, I'm looking at the inside front cover of the book, and here we have units in kilonewton per meter cubed, which will not do us any good because we're in British gravitational units. So we have specific weights in pounds per cubic foot. Water has a specific weight of 62.4 pounds per cubic foot. All right, so we start with our pressure at A, which is 0.6 pounds per inch squared. And we add to that the specific weight of water, 62.4 pounds per foot to the third, times 3 inches. Okay, now we have to resolve something here, don't we? The first problem is we can either change this into feet or this into inches. And which way we do it is not that important. But if we change this into inches to the third, then we'll have inches to the third down here and inches up here, which will cancel to inches squared, so we'll have pounds per inches squared. So let's go ahead and do it that way. So we have to have, we know that there are 12 inches per foot. So to get from feet squared in the top, we know that we have 1 foot per 12 inches. And in order to do that, we have to take both of those to the third power. All right, for our third term then, we have the specific weight of our gauge fluid, which we're told the specific gravity is 2.6. So we can take 2.6 times the same, 62.4, and then we have to do our conversion, which is 1 over 12 to the third power. And then we have to get this height, which is going to be 8 inches times the sine of 30. Okay. Minus gamma of H2O, 62.4 again, times 1 over 12 to the third times our 3 inches is going to equal pressure at point B. So what you can see from this is everything's going to work out. We worked out our units, so our units are going to come out in pounds of force per inch squared, and we're going to have this value plus this value minus this value minus this value. And you can go through and work through the numbers, but it turns out to be 0.224 pounds per square inch equals PB, or it's more appropriate to write it as 0.224 PSI equals the pressure at point B, or in pipe B, I should say. All right? So that takes care of sections 2.4 through 2.7. And I've done an inclined manometer problem for you. If your manometer is just a U-tube, all you have to do is take into account the height differential, but the principles are the same. Pressures are the same at interfaces. Pressures increase according to the hydraulic gradient going down. Pressures, they increase going down according to the hydraulic gradient up, and they decrease going up based on, and as I've said, hydraulic gradient. I do not mean hydraulic gradient, which is something a little different. I meant to say hydrostatic gradient. So as you go down, the pressure increases according to the hydrostatic gradient. As you go up, the pressure decreases based again on the hydrostatic gradient, and the pressure at all interfaces has to be equal on both sides of the interface. So that's it for section 2.7. We'll see you to finish off. We have two more vodcasts for chapter 2, so we'll continue next time.